Hi everyone, we are back and let's do our basically practice exam problem. So let's read our problem. All right, directions, planes, we kind of know what's going on here. So identify the conventional unit cell. All right, so simple cubic, this is FCC and this is BCC. Number of atoms, 1, 4, 2, and the crystallographic directions are planes. So let's go ahead and look at these guys. So I'm going to take this guy right here. What's our finish point? 110 minus my start, which is 111. So what am I left with? 0, 0 minus 1. Makes sense. What about here? So my finish is 0, 1, 0 minus 1, 0, 0. So what am I left with? That's equal to 1 hat, 1, 0. What about over here? So let's go ahead and draw our finish point is going to be 0, 1 half 0, and our starting point is 0, 0, 1. So we're left with 0, 1 hat, 1 half, which is going to become 0, 1, 2 hat. There we go. And then finally over here, what's our kind of point here? Finish. It's a half, 1 minus my start, which is 1 half 0, 0. So that leaves me with over here 0, 1 half 1, which is going to leave me with basically 0, 1, 2. There we go. So we've got them. So let's go ahead now and I'm going to erase all of it. So we've got that vector, you know what PCC, FCC, and all those are. Let's look at our planes. Across my coordinate, I'm going to choose this as my new origin. This is my new x, this is my new y. So what is my plane? Where am I intersecting my x? Never. What about my y? Minus 1, so it's 0, 1 hat. What about here? Again, I'm going to choose a new origin. So I'm going to go choose this origin as well. Get over here. So with this origin, what am I looking at? I intersect x at equal to minus, let's call it a half. So, not x at never. Actually, we'll see that eventually it's going to basically cross x. You could actually see it's going to continue and cross it right there. But actually, it's a little bit of a tricky one. So x is actually a half if you continue on there. But anyways, y, where I intersect y, it's definitely half in my cell. And then finally, if we look at RZ, 0. So you could call this 2 hat 0. There you go. So that'll work because you'll see eventually that it will cross that x-axis. So let's go ahead and start with, okay, are any directions in A close packed? So are any directions in A? Yes, the O is 0, 0, minus 1. What are the close packed directions in A? So in A, my close packed directions are going to be 0. Here in FCC, they're going to be 1, 0, and BCC 1. So those are my close packed directions. In D, draw an FCC conventional unit cell on the 1, minus 1, 0 plane. So 0, 0, 0, 0. Atom, 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 base, atom, base, atom, back. So let's draw the 1, minus 1 plane. So let's see, where do I get my origin? So I'm going to choose my origin right here. And I can go out, out, plus. So I'm going to intersect x here. I'm going to intercept y here. And I'm going to go ahead and just finish that up. So if I did the same thing here, it'd be here and here. So it's going to be my plane. 1, minus 1, got it. Is this a close packed plane? No. And I need to justify that quantitatively. So I see in this plane, I have a plane that looks like this. So corners, and then one here, one here. So my planar density is equal to 2 times pi r squared divided by, this distance is a square root 2. This is a, where a is equal to 2r root 2. So a times square root 2. Calculate this out, it is not close packed. And we know that because in FCC it's only 1, 1, 1. All right. Now, I am looking at an RDF and a PDF. Yay! And you've seen this before. So let's look at these values. So I can tell that, let's go ahead and pull up a Mathematica notebook. Let's quit the kernel. And then let's go ahead and say that my 2.72 is equal to 2. I'm going to solve. 2 times R equals 2.72 angstroms. So we'll solve that in terms of R. And then let's see if that next value set equal. There we go. So I know that this could either BCC or FCC. So if it's BCC, it should be 4 times R divided by square root of 3. That's pretty darn close. So BCC, so I know the integral of this first peak is what? 8, because I have 8 nearest neighbors. That gives me the nearest neighbors. Draw, what is it? A semicrystalline and a amorphous polymer. So my semicrystalline, so this is going to be semicrystalline, going to be sharp peaks, and then my amorphous is going to have much wider, longer peaks and then flats. Excellent. Again, amorphous has more short-range order, less long-range order. Semicrystalline will have more amorphous semicrystalline. All right. I'm going to do my tangent vector coming out this way. So I'm going to start my start here. 1, 2, 3. 1, 2, 3. 1, 2, 3. Oh, sorry. So let's go 1, 2, 3. 1, 2, 3. 1, 2, 3. And then, oops. Let me go ahead and recount. And then I'm going to go 1, 2, 3. So coming out of the board. Coming out of the board. Let's go ahead. Let's recount this. Sorry, excuse me. So it's a little bit kind of funky. This one's coming out of the board here. So out of the page. Actually, that's why. Out of the page, so I need to go here. So let's just start here. So I'm going to go 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So my start to finish, what is that equal to? So this is my start, this is my finish. So it's pointing in basically this direction. So that is perpendicular, so that is an edge defect. I'm going to do my tangent vector here coming out of the board. So I'm going to curl this way, so I'm going to start here, and I'm going to go 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then I did 1, 2, 3. So 1. So again, my start to finish, this is a left-hand screw. That's it. And the other defect, there's nothing there. All right, that's number 1. Not too bad, not too shabby. All right, we'll get into the next one next time. See you then. Thanks. Bye.